In this video, we're going to be talking about levers. There are 3 different classes of levers, and in some of the classes, there are different types of levers. We went into quite a bit of detail about this when we covered the information with the caveman video and together in class. We're going to talk about all those kinds of levers here in this review, but we're going to go much more quickly. Also, bear in mind, I'm not going to require you to know the names of the kinds of. I'm not going to give you a lever and say, is this a first class lever or a second class lever or a third class lever? I think it's important that you know that there are distinctions, but I don't think in 9th grade it's important that you be able to identify which is which. That's something that you may do in physics when you're older. It's something that you may need to learn about in industry if you end up working in heavy equipment or something like that. But it's not something that I need for you to be able to articulate here in 9th grade. So let's start out by talking about first class levers. Let's say I have something that looks like a seesaw, right? I've got my lever arms here. Here's the fulcrum. I'll put an F. And let's say that I have a rock. Here's my rock. It's really a rock. Let's say that this arm is 5 feet long and this arm is 5 feet long. So it would take the same amount of effort for me to push down here as this rock weighs. So if this is a 50-pound rock, I would have to push down with 50 pounds of pressure here. We could figure out the IMA, or mechanical advantage, of this by taking the input arm divided by the output arm. Let's write this down. Input divided by output. So in this case, input 5, output 5. My mechanical advantage is 1. In other words, it's going to take the same amount of force of pushing that represents the weight of my rock. So if the force is the same and the distance is the same and the speed is the same, why would I care? Why would I want to use a lever in this case? Well, you can see that the force is in a different direction. If I push down, the rock goes up, and sometimes it's important to be able to do that because you're in a position that you can't lift up. You need to be able to push down. So that would be a reason to use this kind of lever. There's another kind of lever that's very, very similar. It also has the fulcrum between the load and the force applied. It would look more like this. So here's our fulcrum. Here's our rock. This is the output that we need. Here's our input. I may be pushing down here. But what if this is a 2-foot distance and this is an 8-foot distance? Oops, I could put that right here, 8 feet. We'd figure out the IMA the same way. The input arm here is 8. The output arm here is 2. 8 divided by 2 is 4. So the mechanical advantage here is 4. In other words, I can multiply the force I exert by 4. If this is a 40-pound rock, I only have to push down with 10 pounds of force in order to lift it up. Now let's talk about the trade-off, though. I have to push farther. I have to push down 4 feet while this rock only goes up 1 foot. So as with any other simple machine, there's a trade-off, distance for force. But in this case, it would allow me to lift up something that was too heavy for me to lift up on my own. A very closely related kind of first-class lever is this one. Again, it's a first-class lever. The load and the force applied are on different sides of the fulcrum. But what if my rock is here and I'm pushing down here? Well, this is completely different. I've turned this on its head now. Now I'm going to have to push really, really, really hard for my rock to go up at all, right? This is crazy. Here's 2 feet, here's 8 feet. So in this case, my mechanical advantage would be 2/8, or only 0.25, or a quarter. Why in the world would I want to do that? Well, sometimes we want to trade force to increase distance or to increase speed. Some examples of that are oars or paddles. If I want to paddle my canoe, I want my let's see, I could draw that, couldn't I? If I want, here's my canoe paddle. Hey, this is a pretty decent canoe paddle. There we go. So if I'm holding it, it's rotating around a fulcrum about here as I'm paddling. I want my paddle to sweep through the water at a pretty good distance and a pretty good speed. I'm not going to be able to move my arms and shoulders all that much because I'm up here in a boat, right? Here's my, let's see, that could be water. I didn't intend to draw a boat when I started this video, so now it's probably going to be a really terrible boat. Yeah, it is. It's a terrible boat. But if I'm holding this, I want to sweep a lot of water. I want my paddle to go a long distance. I can apply a lot of force with my shoulders. I want that force to matter a lot in terms of distance. So that's one reason I might want to use this kind of lever in a boat paddle. Some examples of this kind of lever, that the input and output arms may be the same, but we just want to change the direction of force. I mean, the best example of that I can think of is just a playground seesaw, which I think we've all played on. An example here, maybe a pry bar or a claw hammer, a branch cutter, a shovel, anything that we don't mind pushing a pretty great distance in order to get a lot of force without moving very far on this end. Another example of this kind of first-class lever might be scissors. We don't mind pushing really hard together with our hands in order to control the scissors, but we want the blades of the scissors to cut a lot of paper for every time we use them. So that might be another example of this kind of lever. So those are first-class levers. I told you don't have to know their name, first-class lever, and you really don't. It's okay to just know that this is a kind of lever. The ones we usually think of, they have the fulcrum in between the load and the input force. Another kind of lever that also is useful and also we encounter is the kind of lever that may have the fulcrum here, the output force here. Sorry, there it is. A fulcrum there, the output force there, and the input force here. So maybe I want to lift something up like this, but I have to have my fulcrum over here. Maybe I can't get the fulcrum anywhere else. An example of something like this is a wheelbarrow. You can almost imagine this being a wheelbarrow, right? So we use the same thing for mechanical advantage. IMA equals input arm divided by output arm. So let's make this another 10-foot thing. If this center of gravity of my rock is 2 feet out and this is 8 feet, what's my input arm? It's 10 feet. The distance between where I'm applying force and the fulcrum is 10 feet. I can use all that distance for input. 10 divided by what's my output? Hopefully you see that it's 2. So my mechanical advantage here would be, can you see it? Heck, it's 5. It is. That number right there, that's 5. We can change this mechanical advantage by moving my rock, right? The fulcrum can stay in the same place. Everything can stay in the same place. But if I move the rock to in the middle, now the rock is 4 feet out, 4 feet here. My input arm is still 8, but now my rock is 4 feet out. In other words, this is my output arm. 8 divided by 4, mechanical advantage is 2. Just to reiterate, mechanical advantage does not have units because it's not something that we're measuring in units. It's a relationship. It's a relationship of distance to distance or force to force. And if you wanted to look at it a different way, if you said this was 8 feet, 4 feet, 8 feet divided by 4 feet, we would cancel these units, right? So again, we'd come up with a unitless answer. A third kind of lever, it's a little bit harder to visualize, is the kind of lever that we have in our shoulder joints and our hip joints. It's a kind where the input force and output are going the same direction, but I want to put in a lot of force right here, but not much distance, and I want this to move a long way. So, so this is something that like maybe your hip does this. You apply a lot of force, but only a small amount of distance with a muscle to move your hip joint. But then your foot moves fast and it moves far. So that's the kind of lever that we find a lot in our bodies, our shoulder muscles, our hip muscles, or our hip muscles that move our legs, that our leg would be the lever. Our shoulder muscles, our arm would be the lever. Our jaws even work like this. Let's see. Let me glance at my notes to see if there's anything else I want to point out that you really, really need to know for this test. Basically, it's just that you need to know lever arms and fulcrums. Those are the two major parts of your lever. You need to know that some levers change the direction of input force. Some levers don't change the direction, but just change the amount. So we're trading force to increase distance and speed in some cases. There's always a trade-off with simple machines between force and distance. As you finish studying for this portion of the test, please go back and watch the caveman video. Those videos are posted on Google Classroom on the days that we did the initial discussion about the topics. Please go back and look at those. You'll also want to be able to use the term torque comfortably in order to be able to get some of the answers on tomorrow's test. Understand that torque is not a simple machine, right? Torque is kind of a vocabulary term. It means twisting power, and it's something that we use to describe what simple machines do. There's a Science of NFL Football posted on Google Classroom on the day we covered the topic of levers that you may want to go back and look at that talks about torque in more detail.